Hello, guys. People, can you hear me? People attending online, can you hear me? Just a second, guys, please. Do you want me to go through the solutions for homework 7? Okay, so people are they hearing me? Guys. Woohoo. Oh, okay. They can hear me good. Okay. Great. So, do you want me to go? No, I will post them, but I will not post them entirely. I'll just refer to the notes when they're in the notes. If you want to do it entirely, I'll do it now because it's super long. If I do it entirely in the notes. And if I type it entirely, it's going to take me a long time. But many of them are in the notes already. Okay? Is that fine, or do you want me to do it all? I am. I can do whatever you guys want. So if you want me to start with the exercise, I'll do that. But for homework 7, most of the exercises have been done in the lectures.
Can you just put like which lecture?
Yeah, I did already.
Oh.
Is that okay?
Yeah.
If I tell you where. No, I'll put the solutions. Yeah, every question that I did not put, I'll just let you know where to find in which lecture. Is that fine? Or do you want me to do them all? Because I'm not rewriting everything. Rewriting everything. Just great. Okay. Maybe let me go through question 2 of homework 7 again, because I think it's important. And question 2 of homework 7, exercise 2. Exercises 1 and 2. I mean, I feel they're a bit important. They're very important, yes. That's why I want to go through them again. People here can hear me? Yeah, they can hear me. Okay, great. Thanks. Okay, so what do you guys want to start? The exercise sheet or homework 7?
What's the first?
Homework 7. Okay. Okay, so let G be a group. I've done these like 55 times so far, so it's a sign that they're important. Okay, so these 3 questions are important. So let G be a group, and H a subgroup of G. Show that G acts on S, X, which X inverse, and X belongs to G transitively. I G X H X inverse. G X H X inverse G inverse. And stab of the element H is just the normalizer. Okay. This is very, very important. So okay. So first of all, I need to justify that G X H X inverse, G inverse belongs to H. I mean, this is clear. Right. Belongs to S. Sorry. What is that? So just G X H G X inverse belongs to S. Could you please quickly recap that? What happened? Okay. gxh gx inverse, then that's clearly belong to S. Now, why this is an action? What do I need to check for this to be an action? How many axioms? How many definitions? 2 definitions. So what is EG star xh x inverse? That takes what is EG of that? Is it just EG xh x inverse EG inverse? Okay. Now let G1 G2 G. What's G1 star G2? It's just G1 star G2 x. It's just G1 G2. Inverse. Okay. Right? Is that right? Questions from people attending? No? Okay. Now, what is the stabilizer of H? How do I compute? Or why is this action transitive? Why is this action transitive? There's only one orbit, so how do I prove that? What element do you suggest I take the orbit of? I mean, all gonna be the same, but what's the easiest one to manipulate? No, well, orbit is an element of S.
H.
H. Yeah. You mean X equal the identity? Yeah, for X equal the identity, you get H, but the element is H. Yeah, exactly. So the orbit of H, what is that? This is just G star H, as G is in G. So just G H G inverse as G is in G, which is just S. Right? Agree or not? This is just S. Hence, this action is transitive. Okay, and what's the stabilizer of H? How do I write down the stabilizer of H? I just write down the definition. Tab H is equal to what? Everyone? So just this G and G. Such that G star H is equal to H, which is just G and G, such that GH in inverse is equal to H. And this is equal to the normalizer of G, right? Now this gives me a proof the normalizer of G, the normalizer of H and G is a subgroup. Yeah.
Which part specifically shows that the action is true?
Here. What's the orbit of H?
Okay, then it's
The whole set. Okay, so you have only one orbit, which is the whole set. Okay, yeah.
But how do you know to look at the orbit of H?
You can do any other element. Just H is the simplest one.
Like what other one?
XH X inverse. Any XH X inverse will do it. So you'll get that it's G X H X inverse G inverse.
Oh, like any element in
S.
S.
Exactly.
Such-
Yeah. 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 Provided that G star S, provided that your action is well defined, that it maps any element in S to S. Okay. Yeah.
So that one.
Yeah, exactly. Exactly. Otherwise, you would have G X H X inverse G inverse as G's in G. You stabilizer? No, I give to you H. I give you find stab H. If you take stab XH X inverse, it will be different. It will be the conjugate of NGH. So I told you compute stab H. I gave you H. I computed explicitly. Okay. So the normalizer of G and H is a stabilizer of H. The normalizer of H in G, sorry, is the stabilizer of H under this action. Okay, and why is the normalizer a subgroup in that case? Why is it a subgroup of G? Yeah.
Because it's expressed as a stabilizer.
Exactly. Very good. Okay. If you want to show that something is a subgroup, it might be a good idea to express it as a stabilizer of an action. Okay. Great. And how many distinct conjugates does H have if this number is finite? It's the index of the stabilizer, right? By the orbit stabilizer theorem, that the index of stab H in G is the size of the orbit, which is the number of distinct conjugates of H if this number is finite. For example, if G is finite, and that's what you get. Okay, is that clear? Is that good? Any questions on this? Yeah. Yeah. Why? Because a group action must map to X.
Okay, so the beginning is just really like
You check that this is a function, right? I cannot tell you pick X, pick F.
like I get all like proving that it's a blue faction and then you do orbit and this one is just like this and like the first statement did like
It's
to do the rest.
exactly different. So for example, you can figure the function from X to X squared maps R to negative M. That doesn't. First, you have to check that your function makes sense. And
Okay. Does it always have to do that?
yeah, because it's not always obvious. Here, it might be more it's obvious in general, but in general, it's not obvious. If you remember the proof of Cauchy's theorem, then we had to do some work to show that it was an element of the set, exactly what you did with the group action. Yeah. Exactly. Exactly. Okay, great. Let's move to the second question. Second question, which is also important. So let N be a normal subgroup of G. Show and G acts on N by conjugation, and that the set. By the way, some people told me they don't like a practice final, but in general, do you prefer one? What is the vibe? Do you like a practice final? Okay.
Yeah, or just practice questions from the topics that are going to come.
No alternative.
Yeah.
I mean, I can post questions as you said, but it's gonna. I mean, yeah, but the practice final is not gonna be the same questions number change. That is not gonna be the case. I might do a session, but I won't type the solutions. Yeah, and then on Thursday. Yeah. Yeah, I mean, yeah, no. Pardon me? No. I want you to be ready and then to study. I won't do a practice. I won't give you a practice final like 2 weeks. Otherwise, it's useless. Otherwise, it's too useless. I can just give you a problem. I give you a practice final on Wednesday. You study, you do it, you sit down, you do it for 3 hours. It would be a good practice for what the final will look like. And then you do a small prova, before your final. Okay, I'm gonna post it on Wednesday. I mean, you could not do it. It's not that if you don't do it, then you'll do bad. There's nothing that says that. And if you do well on the practice final, then you will do well on the exam. But again, it will give you the idea of the structure. And you'll have to sit down 3 hours. Maybe it's a bit longer than usual. So I'll put it, you sit down for 3 hours and a half and make sure you get the questions. It's going to be 7 questions. In the practice, I plan to do 7 questions. And the range of topics that is covered is almost the same as the one in the final. It's not exactly the same, it's almost the same, but you have to sit down and do them. posting them earlier is of no use. You prepare and then I don't want you to look at the practice final and then prepare, because if you do that, it's gonna go terribly. I give you like the practice final before you finish your studying, the thing's gonna go terribly. I can assure you. Because you will go and study the practice final and you'll just know how to do the practice final. That's what will happen. And then you go on the exam. I switch the question a little bit. It's not gonna go well. So I mean, if people want me to post one, it's because I've had a huge demand. Students asking me whether I can post one. Sure, I can post one, but it's gonna be on Wednesday after the lecture. Also, like after the lecture, it will be released so that you try it, and you try it on your own. Sit down and try it on your own. G acts on it by conjugation, and then the set. I mean, I personally believe you don't need one. My personal belief is you don't need one.
As long as we do the notes and the homework. And
You're fine. Yeah, you're fine. My personal belief is that you don't need one. And then they said, I was talking to someone and I told them if I want to do a practice final, I'll usually make it a bit harder, because if the practice final is a bit easier, everybody will say, oh, the practice final is easier than the actual exam. So this is why I don't like that, but we'll see. Let me set a fixed point of this action is an intersection that okay, let's prove this. Let n be a normal subgroup of G. Show that G acts on n by conjugation. Can you sorry, my friend just logged on the thing, so okay. Okay. Hi, Adam. Okay, so let n be a normal subgroup of G. Show that G acts on n by conjugation. The set of fixed points of n intersections at G is the set of fixed points of this action is n intersection Z. So first of all, what is the action of conjugation? What do you have to do here? So things like these two questions could be easily questions on your final. Easily. Like I see myself putting them. And the one after. I've done these two like 25 times so far. How do we start?
No, it's a group.
Yeah, but okay. So what is conjugation? So n is in n, and G is in G. What is the conjugation? What is the conjugation here? Okay. Now I say show that G acts on n by conjugation. What do I need to show about this G inverse? Very good. But what do I need to show? Where does G inverse belong to? And why is that? Right. Thanks. And G. Now you can define an action. G cross n. N. Take G n. G star n. Which is equal to G n. Okay. Now you have a map that you're sure that if G is in G and n is in n, then G star n is in n. That you made sure. Now what's the second thing you need to show? That it's an atom. EG star n, what is that equal to? This is EG n. EG inverse is equal to n. Okay. Now what as well? Let G1, G2 be G. G1 star G2 star n, what is that? Just G1 star G2 n inverse. G1, G2, and G2 inverse, G1 inverse. Boom. Right? So this is a group action. What is the set of fixed point of this action? Anybody wants to help? How do I find the set of fixed point? What does it mean to be a fixed point? The orbit is a one has one element, which is itself, right? And in n, the fixed point. If and only if G star n is equal to n for all G and G. If and only if G and G inverse is equal to n for all G and G. And only if G n is equal to ng for all G and G. If and only if n belongs to n intersections of G. Okay. Any questions, people attending online? Oh yeah, thank you very much. Okay, great. So that's a question. Great. Here? Here? Do you agree with this?
Yes.
Yeah, you agree that this means that n belongs to ZG? If I raise this.
Yeah.
Where does n belong? Little n belong to? Okay. Is that clear? Clear? Everybody, is it clear? Yeah. Okay. Great. Let's move on to the problems I have. Let's see. Did anybody have a look at them? No one had a look. How were they? Were they were not bad, were they?
No, they're really.
You should expect the same level of defining. And a lot were close to the homework, right? A lot were close to the homework. So my handwriting is not best. Oh man, what happened?
Hey, that's your.
No, but the Wi-Fi was cut. I don't know why. Okay, now let's a lot of them are of the same level of the final. You can expect them to be of the same level of the final exam. And they don't come really, there's nothing out of reach of your homework. Great. So which one do you want to start with? Let's start with something you know how to do. Let's start. Did you guys have a look at them or not? No? No? Okay. Let's start with exercise 2. Exercise 2 is nice. I mean, okay, so exercise 2. What does it say? Let G be a group of order 6. Show that G has a subgroup H3 of order 3. And subgroup H2 of order 2. And show that H3 is normal. This is a perfect example. This is a perfect type of question. It revises everything. You have to do everything. You have to study. You have to know many theorems to do that. Show that G is subgroup H2 of order 3 and a subgroup H2 of order 2, and show that G H3 is normal in G to show that if H2 is not normal, so that H2 is normal in G, sorry. Whatever it's that. Then G is isomorphic to C mod 6C. Show that if H2 is not normal in D, then D it doesn't work. Typical question. It involves like many theorems, Cauchy's theorem, anything with subgroups and normal subgroups, the product HK of groups, and then all the theorems, many of the theorems you've seen, and all of them are one after the other. You have to apply them one after the other. Great. Let's do the first question. Show that G has a normal subgroup H2 of order 3 and a subgroup H2 of order 2, and show that H3 is normal in G. What do I use here? Cauchy's theorem. Very good. Oh, very good. My Cauchy's theorem. Equal to 2 times 3. These are primes. 3 are primes. G has an element X, well, has an element of order 3. Hence, a subgroup H3 of order 3. And G has an element of order 2, hence a subgroup H2 of order 2. Okay. Show that H3 is normal in G. How do I do that? Yes. Take the subgroup generated by this element. What is the size? So you have an element of order 3, right? What's the subgroup generated by this element? How many elements does it have? Say X has order 3, okay? What is the subgroup generated by X? 1, X squared. What is the size of that? 2.
6.
Pardon me? Because if you have an element X of order n, then the subgroup generated by X has size n. Okay? This was a midterm question, no? You had something like that in the midterm? No? Yeah, I remember that, yeah. Okay, great. Now, why is H3 normal in G?
The index.
The index is 2. Very good. H3. It's 2. So the H3 is normal in G. 3 marks. This question will be on 3 marks. 1 mark, 1 mark, 1 mark. Yeah.
You also do Sylow's third.
Sylow's third theorem, very good. So you say that n3 divides 2, and n3 is congruent to 1 mod 3. Exactly. Very good. Yeah.
Since the next at H2, H3 subgroup of G and that G is equal to H2 times it.
Oh, here?
Yeah.
Here? Okay. Okay, so
Or it actually,
before. It's on part 1. Maybe let's add it here. Show
Well,
that.
yeah.
Very good. Show that H2, H3 is a subgroup of G and G equal to H2, H3. Okay. Now, how do I show that H2, H3 is a subgroup of G? Both of them are subgroups of G. Now, how do I show that the product is a subgroup of G? What theorem did you prove in the homework? That if one of them is normal and the other is a subgroup, then the product is a group, right? Since H3 is normal in G, and H2 is a subgroup of G, and H3, H2 is a subgroup of G. Right? This is homework 6, maybe? Homework 6, something like that. Now, why is G equal to H3, H2? How do I find GCD of the size of H3 and H2 is 1? Yeah. So I compute the size of H3, H2. This is so since 2 and 3 are co-prime, what is the intersection of H3 and intersection H2? 1. This is 3. It's 2 times 1, which is 6. So H3 is a subgroup of order 6 in G. What is the size of G? 6, which is equal to the size of G. So G to H. Okay? Great. So let's erase that. Let's do the second question, number 2.
Sorry, when you say that G is equal to H3, H2, like in the question, then you're asking us to show that they're the same size.
No, that they're equal. Yeah, exactly. They're equal as sets and as groups.
And you can show that by showing that they're the same.
Exactly.
Oh, because one's a subgroup.
Exactly. Now, you can show that by the same size, but I want to show it's a subgroup first. Because I can switch the question. I can tell you show something is a subgroup, but there's not necessarily equal to G.
Right.
Okay. Now, let's do, see, these are perfect questions. Perfect, short, cute little questions. Nothing is long, nothing is great. Now, show that if H2 is normal in G, then G is isomorphic to Z mod 6. How do I do that? It's also one line. If H2, well, not one line, then G is equal to H3, H2. G is equal to H3, H2. H3 is normal, and H2 is normal by assumption. The intersection of H3 intersection H2 is equal to the identity, right? So this is isomorphic. H3 times H2. Homework 8, right? You remember that? Now H3 has order 3 and H2 has order 2. So H3 is isomorphic to what? Z mod 3, very good. And H2 is isomorphic to what? Chinese remainder theorem, since 2 and 3 are co-prime, what is this isomorphic to? Very, very quick. There is just a bunch of theorems that you need to apply quickly. Yep.
Can you just explain why one has to be normal?
For it to be a subgroup. Yeah, so just write down, you want it to be closed, okay? It doesn't have to be. It's not that it has to be, but it's enough that one of them is normal. So take two subgroup HK, right? HK, and suppose that, HK, H prime, K prime, okay? And suppose that K is normal. Now, HK, H inverse, will be equal to some K2, right? So this HK, you can replace it by, oh man, sorry. Let's switch it. So H prime inverse is some K2. So this KH prime, you can replace it by, wait a minute. Oh, sorry. I just messed up the order of things. It doesn't matter. So KH prime inverse is equal to some K2. You agree with this? Because it's X, K, X inverse is equal to, belongs to K. Okay, so KH prime is equal to K2 multiplied by H prime here. Multiplied by H prime here. So you get KH prime is just H prime K2, right? And then you have H and you have K prime. This is in K and this is in H. Now, if this is not, if you don't have a way to switch these two, then you want to have a subgroup. Okay. Normal is not necessary, but it's indeed sufficient.
What is the instance with?
Do you want a place where it doesn't work? Sure. Pick two non-normal subgroup, let's say H2 and S3, 1, 1, 2, and 1, 1, 2. Okay. Take the product of these elements. So you get 1, 1, 3, 1, 2, and you have another element.
Oh, I can't do that.
Okay, so it's 1, 2, 3, and 1, 3, 2.
Yeah.
I think so. 1, 2. Yeah, so you have 1, 2, 1, 3. I mean, look at the size of the sets. H intersection K is 1, right? H times K. This formula holds for sets. This doesn't. You don't need them to be subgroups in this case, I think. Okay, you don't need them both to be normal for the HK formula. So you have a something of size 4, which is not a subgroup. Okay, or just write them down.
Right, okay.
Write them down. H times K. So what is, you're going to write them down or that's good. Just write them all the possible products. You have 4 of them. And they're all distinct. It's not a subgroup because it has size 4 and it's 3. Okay. Yep. So that this works. This formula works. We practiced in homework 8, right? You remember that? In the order PQ question. In the PQ question, right? There was one question where you had 2 subgroups of primes P and Q that are distinct. And then you had to show that. By homework or by notes or class theorem or anything, as long as it's not the goal of the question. Okay? As long as it's not the goal of the question, then you can use that. Okay, great. Now, show that now if H2 is not normal, then G is isomorphic to S3. I mean, are these long questions or not? They're not long, but yeah.
We have to cite specifically where, like homework.
No. I mean, I just happen to remember that. Okay, because but
Yeah.
you don't have to state them. I just stated for you.
Okay.
Yeah, imagine like homework 8 problem 1 recited, you know. Recite homework 8 problem 1. So yeah, it's not gonna be I'm just saying for reference. I mean, I don't remember what question even this is. No, it's so. Great. Now 3. Show that if H2 is not normal, suppose that H2 is not normal. Show that G is isomorphic to S3. How do you do that? Can you guys hear me, those who are attending online? Now, how do I do that? How do I do that? How do I get a homomorphism from G to S3? I need a homomorphism of H, right? G acts on G mod H2. So you take a coset G, an element G. Right? This action induces a homomorphism from G morphism rho, let's say, from G to S3. And the kernel of rho is contained in H, right? H2, sorry. Right? Agree or not? So far, so good? So far, so good. What is the size of H2? 2. What is the size of H2? 2. So kernel of rho, what can I say about that? It's either 1 or H2. Agree or not? Kernel of rho is contained in H2. What are the subgroups of H2? It's 1 and H2. Agree or not? H2 has size 2, right? Since H2 has size 2, a row ZG or a row is what? A row is H2. One of them is not possible. Which one of them is not possible? Why H2 is not possible? Agree. Very good. Are we good? H2 is not normal, so the kernel, but H2 is not normal. H2 is not row. It's different than H2. So row is 1. So what can I say about row? Row is injective. Very good. Row is injective. What is the size of row of G? Row of G has size 6, right? Since row is injective. Agree or not? Everybody, since row is injective, row of G has size 6. Since S3 has size 6, then row of G is equal to S3. So row is surjective. Row is injective and surjective, and it's a homomorphism. What can I say? Row is an isomorphism. So row from G to S3 is an isomorphism. Very good. That's a question. Could be a question on your final. Okay. That could be a question on your final. Different numbers, different things. Yeah. Group action and plasma homomorphism. From G to the symmetric group on G mod H2, right? Now the symmetric group of G mod H2, how many elements do you have in G mod H2? 3. Label the cosets 1, 2, 3. Is that clear? Yeah. Okay. Is that clear? Questions like that are very, very, very fair game. I can change numbers, I can give you different things to do, but all in this spirit. Yeah.
Would you give us the hints that you gave on
Yeah.
this?
I give hints in the finals, so like I give hints. A bit generously to say. Okay. It's a bit, yeah, it's a bit yeah, maybe I shouldn't have done that, but it's that yeah, as long as you get it, I'm very happy. And some things you have seen already, and I give you hints in case it's so again, if you have a blank or something, it gives you a small push. Yeah.
About group actions.
Yeah.
In the exam, will we have to make our own one, or will we be given to?
So if you have to make your own, it's something that you have seen. Okay, I will not give you a group action that you have not seen where you have to make up your own. So no, I mean your own should be the ones that you have seen. Okay, I won't give you something very weird. Okay, I won't give you. You won't have to make up something very weird. Like Cauchy's theorem one. If I were to examine it, I would give it to you. I would say, so it's a group action. I won't tell you make it up on your own. Yeah. So yeah, this is for instance, an example. If you need a homomorphism from G to S3, what's a nice way of getting a homomorphism from G to the symmetric group? It's just a group action of G on 3 elements. Okay, now you have a subgroup of order 2 in G. So the index of this subgroup is 3. Oh, well, let's try the coset representation. Let's see what we get. This is the coset representation, right? S3 has 6 elements, but G mod H2 has 3 elements. S3 is just sim G mod H2, right? If you want isomorphism from S3, you have an action on n elements and see what you get. Yeah.
One thing that the kernel is identity, we not just first isomorphism.
Yeah. Also, you can use it for isomorphism here. Yeah. You could say that G is isomorphic to row G, which is S3. Yeah. Okay. These are very, very fair questions and very, very quick questions. And I'll give you hints if you have something like that. Most of the times I'll be giving. I think the final has 3 or 4 hints. So it's like, and 3 or 4 hints is like, you know, take it, you know. This is how you do it, you know. This is how you do it. But again, you should have studied it. You should study it. I give you this. I give you this small push at the beginning, then you should be able to get it with it. Yeah. It's a theorem. It's a theorem, yeah. Rho is injective if and only if the kernel is the identity. If and only if. Both of them. Yeah, so again, I am not again it's not the yeah. So everything that was judged hard by the 4 of us, I gave hints. Okay. Everything that was judged not easy, even if it's bookwork, I gave hints. Okay, so it's yeah.
You wouldn't have proofs though, right? Like,
Maybe I do. I do. In one of the proofs, I do give it. Hint. Do it this way.
Is it like hint use Koji or hint question 6 from the 8?
No, but like, you know, it's I would say hint use Cauchy's theorem. Yeah. For example, that thing. Yeah, I mean it's a I know it's a bit harder than usual, so I'm
With a lot less stress.
yeah, no, well it doesn't mean that you have to go relax. Like there are 7 questions, there are definitely not 7 hints. Okay. 7 questions.
Part ABC.
I mean, there's not 1 hint per question, or if I can, that's what you're asking. Oh yeah, many questions have 3 questions. I think I put 3 hints, maybe 3 or 4. I can't remember. 3 or no, and they're not the hardest. No, the hints one are not the hardest one.
What would make sense? But
No, because if it's hard, sometimes you may not get it, even if I give you a hint, right? But I think there's nothing really hard. There's nothing really difficult, actually. Seriously, like there's nothing really difficult. Everything you have seen the likes of questions like that. Okay, great. For example, use Cauchy's theorem is just as show that G has a, for example, show that G has a subgroup of order P. And so, for example, if I give you a question like that, for example, if I were to give a hint on this one, so G has a subgroup H2 of order 2 and H3 of order 3, and show that H3 is normal. If I were to give a hint, Cauchy's theorem, and the other part B, what is the index of that? Okay, so like, you know, it's really like, you know, like you're in front of the goal, you know, then you have the keeper, and then I dribble the keeper and I pass it to you. Okay, and then you have to score. Okay, so it's some of the hints are like that. Okay, so oops. Okay, great. Let's do the second part, the third question. Or which one do you want to do? Exercise 5. Write down explicitly or subgroups of order 8 in S4. You've done it? No. Ready? No, you have to know how to write it. That's a fair question. That's a very fair. Yeah, please don't do it. Okay, sure. I'll not do it
See,
anymore.
Yes.
You want me to do
in
it?
this room.
Yeah.
Verbalize it.
You want me to do it or? Any? No, just blink if you want me to do it. No, actually, if we do it, just blink. Okay. Great. Now, you want to do well, 5 and 6 come together. So 6 is interesting. So 5, I'll have to do it. Write down explicitly all the subgroups of order 8 and S4. The one group they are isomorphic. I'll have to do it because I want to do 6.
So we are doing.
Yeah. For example, if this were to go on the final, I'll tell you write down all the subgroups of order 8 in S4. If I were to give a hint, what do I say? Symmetries of the square and Sylow's second theorem, for example. Sylow's second and third theorem. This might be, for example, or said.
Rotation.
Pardon me?
Rotation.
No, I mean, I will tell you, write them down. I will tell you, list the elements explicitly, for example. If I wanted to write a subgroup explicitly, I would tell you to do that. In S5, in S4, in S3, in Z16, or in anything. If you need to write a subgroup explicitly, then okay, great. Write down all the subgroups for the in S4. So by Sylow's second theorem, how many subgroups do I have? So 20. Okay, let's start first with one subgroup. Which way do you want to label your square? 1, 2, 3, 4. Okay, I look at the symmetries of this one. Let's call it H1. What are the symmetries of this one? I have the identity. What's the second one? 1, 2, 3, 4. The rotation of 90 degrees. What's the second one after? Everybody, can you help me? 1, 3, 2, 4. Then what as well? 1, 4, 2, 3. What as well? Now I have the reflections.
1, 4, 3, 2 and 1.
1, 4, 3, 2. Sorry, yes, thank you. 1, 4, 3, 2. Now I have the vertical reflection. What is a vertical reflection? 3, 4. Now the horizontal, what does it do to 1 and 4? It switched them. 1, 4, 2, 3. Now the diagonal one, you have the diagonal passing through 1, 3. What does it do? 2, 4, and then 1. Okay. Is this subgroup normal or not? No. Okay. Now write down another subgroup. Okay, I will just label the square now. 1, 2, 3, 4. Write down the subgroup of this. And H3. 4. Okay. Why are these the only subgroups? By what theorem do I know that there are 3 subgroups, or what? Well, how? What theorem tells me Sylow's third theorem? By Sylow's third theorem, how many subgroups I have? I have 1 or 3, right? If I have 1 or 3, and I found 3, then then it's 3, right? No, I mean I found at least 3, right? If you found 3, or at least if you found 2 of them, then you have 3. Or if one of them is not normal, then you have 3, right? All of these ways. By Sylow's third. And 2 belongs to 1 or 3. And this, since we already counted. Okay. Great. Now to what group they are isomorphic? To what group? D? D4. No, the subgroups are isomorphic too. They're all isomorphic. They're isomorphic. Okay, great. Any question here? Yeah. No, I mean if they're all conjugates, right? Then they're all isomorphic to each other. And then this is how you construct it, right? Exactly. No, if they're, so all the Sylow's P subgroups of a group are isomorphic because they're conjugated. And now how did you construct one of them? By just looking at default. Okay? Yeah. And to the number of Sylow 2 subgroups. Right? 24. Okay. You don't have to, I don't think there's a question. So Sylow subgroups. That is not the proof of the third. Okay. But I mean it is just
But that's just an application.
And you know that the other possibility is one, because it's like 2 to the 3 times 1 also. So it could be 1. Like,
So-
I don't understand why it isn't only 3.
It's 3. And 2 is congruent. Monthly. So it's either 1 or 3. Okay? And you already found 3, so it's 3. You already eliminated 1. If you eliminate 1, then it's definitely 3, and you found them all.
So are there ever like instances where it isn't like M, where it's not M? And
Yeah, where it isn't the other one. Yeah, if you pick 3 that is not prime, for example. 2 cubed times I don't know, times 35. Right?
smaller numbers.
It's up. No, so yeah, it could be n2, could be 1, 3, 5, 7. So what did I say? So it's 2 times 35. So it's 2 cubed times, oh man. Anyways,
That's
But-
just Sylow's third theorem.
yeah, exactly. You
Okay.
just apply by Sylow's third here. In that case, since 3 is prime, it's either 1 or 3. Okay, great. Now, exercise 6, which is a very interesting question. Also very, very interesting. Let G be a group of order 8. That's very nice. Very nice. Let G be a non-abelian group order 8. Question 3 is ready. 6. Show that ZG has just 2. 2. Show that if G has at least 2 elements of order 2, then G is isomorphic 54. Very, very, very nice question. First of all, why is ZG? Why does ZG have size 2? Again, should be very quick. Not very quick, but elimination. Okay. So can ZG have size 8 if G is not abelian? So we know, so first of all, by Lagrange. Agree? G is not abelian. So that G is different than G. Okay. Agree? Now, why is ZG different than 1? Should apply a theorem. P groups, exactly. This is a 2 group, right? This is 2 cubed. 8 is 2 cubed, for example. And 2 is a prime number. We know that the center of a P group is non-trivial. ZG is different than 1. Since G is a 2 group. It's prime. And you know that centers of P groups are non-trivial. Great, now I have 2 and 4. Why could I eliminate 4? See, is any of these questions very long, for example? No. But you just have to apply the right theorem and the right result. Why is G not equal to 4? The ZG is not equal to 4. The size of it. Well, not exactly 4 is not prime, but
It's because of the index.
index, exactly, because if it has size 4, then what would the index be? 2. We know that if G mod ZG is cyclic, then G is abelian. Exactly, so G is not abelian. Implies that G doesn't have a prime index. So that G doesn't have index 2.
Why does it sound like this?
Because if G mod ZG is cyclic, then G is abelian. Right? So if G mod ZG has prime index, if G mod ZG is prime, has prime size, then it must be cyclic. ZG is always normal, right? What homework is that? I don't know. Homework 6, maybe? So ZG does not have a prime index. G. This implies that ZG is different than 4. Otherwise, the index would be 2, right? If the index is 4. Great, so what are we left with? 2. So ZG is 2. Yeah.
Can you just walk through how you got that from G is not abelian to the last?
Here?
Yeah.
Okay, you know that if G mod ZG is cyclic, then G is abelian. Agree? So if G mod ZG has prime number of elements, then it must be cyclic. If, say, G mod ZG has size P, then it must be isomorphic to Z mod PZ, which means it's cyclic, which implies it's cyclic, which implies that G is abelian. Is that clear? 100%? Homework 6. This is one question, actually. Homework 6. Show that ZG cannot have prime index, I think, right? Yes.
So like we have to remember like everything.
Yeah. Yeah, you have to remember everything. You may use them. I may ask you to redo it. Yeah. You may, yeah. I question every single thing. So every statement is can be evaluated. I can ask you to prove the same thing. Of course, if I ask for the same thing, don't say homework, right? But if you need to use it, you can say I've seen it in the homework. Yeah. Or homework, or I know this, we know this, we've seen this. Anything like that. Yeah.
I think I deduced after that they asked me with everything and go the other elements. Don't like if you have a hunch of which one it is, you can prove it by showing that the other. Like,
The thing is that you don't know the structure.
yeah,
You don't know the structure of ZG. So you want to show that ZG has size 2. Oh, you mean this one? Or you mean doing this one by just calculations?
yeah.
Doing this one by calculations. So you must have an element of order 2. And you must have 2 elements that don't commute. Yeah, it might take some time. Might take. And I'm not sure how to do it this way. I'm not sure how to do it. Okay. I'm not sure how to do it this way. But this way, it's very quick.
Yeah.
Great. Now, show that if G has at least 2 elements of order 2, then G is isomorphic to D4. Also very, 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 I don't want to say it's easy, but it's also it's 2-3 steps and you're done. And then 2-3 steps that you have seen. maybe the first step is the hardest one.
G. A group of order 2.
Yeah, if G, so let's say, suppose that's a very good start. So let's say that I want to show that G is isomorphic to D4. If you look at the previous question, we've proved that every subgroup of D4 of order 8, of S4 of order 8, is isomorphic to D4, right? The subgroups of order 8 and S4 are all isomorphic to D4. So if you manage to find an injective homomorphism from G to S4, you're done. Agree? Yeah. No, if G, it has 5. And I'm saying if G has at least 2 elements of order 2. At least 2. So if you have at least 2 elements of order 2, then you must have 5 in that case. Because D4 has order, that's a good question. So if I find that subgroup of order 2 that is not normal, and I let G act on this subgroup of order 2, on the cosets of this subgroup of order 2. What is the index of this subgroup of order 2 in G? 8 divided by 2, which is 4. So I get a homomorphism from G to S4, whose kernel is contained in the subgroup of order 2. If that subgroup of order 2 is not normal, then the kernel must be 1. So this homomorphism must be injective. So G must be isomorphic to a subgroup of order 8 in S4. And all of them are isomorphic to D4. And then you win. Now what's the key here? The key is showing that G has a subgroup of order 2 that is not normal. This is where this fact comes into play. Okay? ZG has order 2, and G has at least 2 elements of order 2. Agree? So if you have 2 elements of order 2 and ZG has order exactly 2, one of these 2 elements must not belong to ZG. Agree or not? You have 2 elements of order 2 and ZG has order exactly 2. So at least one of those 2 elements. So one of those elements must be the generator of ZG, right? Order 2, say A and B. We know, or without loss of generality, did you ever use this word? I think it's the first time I use this word in this class. Without loss of generality, meaning you can assume that G is generated by A, right? You can assume that G, sorry. Agree? Because ZG has order 2, you know this, and you have at least 2 elements of order 2. Yes or no? You have at least 2 elements of order 2 in this group, and you know that ZG has size 2. So one of those 2 elements of order 2 must be the generator of ZG, and the other one will not belong to ZG. And B doesn't belong to ZG. Agree or not? Is that clear? Is that clear? Yeah or no? So one of those 2 elements must not be in ZG. Now I claim that the subgroup generated by B is not normal in ZG. Is not normal in G. Why is it not normal? Yeah. So ZG has order 2, right? And you have at least 2 elements of order 2. One of them must be the generator of ZG, and the other one is not, because you have at least 2.
If it's not
Doesn't belong because ZG has 2 elements, 1 and 8.
oh, one.
Yeah, identity and right? Now, why is B not normal in ZG? Yes.
It's not in ZG. So it would have to be to
Doesn't necessarily, why is that?
commute it.
But why is that? In general, you might have a normal subgroup that is not in the center. Take S4, for example. You have the line 4 group, the 3 2x2 cycles and the identity, they form a group, but they don't commute. The center of S4 is 1. The converse is true. If you have a subgroup of ZG, then it must commute, then it must be normal, yes. But if you have a subgroup that is normal, it doesn't mean it's contained in ZG. Why is that the case in this case? Why, if this subgroup of order, yes? Yeah. So take, for example, Z2 for a Z2. It has three normal subgroups of order 2. No, but what? Yeah, but why in that case it's not in the center? Why that case that is not normal? The center has 2 elements. They could have 3 subgroups of order 2. Yeah, they could have it. But if they were normal, they wouldn't be conjugate to each other. The subgroups wouldn't be conjugate to each other. If they're all normal, yeah. If you have 3 distinct subgroups of order 2 and they're all normal, then they're not conjugate to each other. You can, but they won't be conjugate to each other. No, so take any subgroups of order 2, say Z2 cross Z2, right? It's an abelian group. Take the 3 elements of order 2, they generate each subgroups of order 2 that are normal, but they're not conjugate to each other because it's abelian. A subgroup is only conjugate to itself. Yeah, but why? Why? Okay, we're starting to get there. Well, but it's not necessarily A. It's not necessarily A. Okay, so B would have to be G. Okay, no, we're getting close to that. So suppose B is normal. Very good. Suppose B is normal. Yeah, we're starting. Very good. Then GBG inverse belongs to. Agree? Now, could it be the identity? Could GBG inverse be the identity? No. Right? Because if GBG inverse is the identity, this means that B is the identity.
Yeah.
Okay? GBG inverse. And for all G and G, sorry, for all G and G, GBG inverse belongs to this. Since GBG inverse is different in G, then GBG inverse is equal to B for all G and G. This implies that GB is equal to BG for all G and G. This implies that D belongs to center of B. So if you have a subgroup of order 2, it's normal if and only if it's a subgroup of the center. But that doesn't hold that doesn't hold true for subgroups of other sizes. Now that's a contradiction because B doesn't belong to G, then G. By assumption.
Because B doesn't equal A.
Because B doesn't belong to A. Exactly. Right. Exactly. Yes.
This might just be using this fact, but like B must have made a C classes and then
Very good. Very good. So that's another. If B were normal, then the subgroup B is a union of 2 distinct conjugate C classes. One and the other one must be B. It's a singleton conjugacy classes, so it must belong to the center. Very good. Yeah. Very good. Very, very good. Very nice. Okay, so contradiction. Okay, so B is not normal. What do you want to call B? Did I call it something? Let B equal H, say. G, the action of G on G mod H induces a homomorphism. What is this action? Always presented. It's very precise. G x H, the G x H, induces a homomorphism from G sim G mod H isomorphic S4, whose kernel morphism row with her row contained H. H is not normal, so what is and H has size 2, so what is the kernel? H has size 2. And H is not normal in G. So what? H is not normal in G, so her row is, what is her row? In that case, everybody? EG, identity, everybody? Are we good? Any questions on that? Her row is a subgroup of H. H has size 2, but it's not H because H is not normal. So her row must be 1. So row is injective. A row is injective. Hence, row G is isomorphic to a subgroup of order 8 in S4. Now, all the subgroups of order 8 in S4, they are isomorphic to what? Hence row G, so G is isomorphic. Row G is isomorphic. Yeah.
Why do we say that they're isomorphic to D4? Is only one labeling considered D4?
This way it depends on the labeling. It depends on the labeling. That's why I don't prefer to write D4 is a subgroup of S4. Okay. D4 for me is an absolute, but you can write it, it's okay. As long as you list the elements and you choose your labeling. Yes, because D4 you can label the rotation as R, 1, 2, 3, 4 as R, and one of the reflections as S. Okay, they're all the group of symmetries of a square. You can label them A, B, C, D, right? You can label them M, N, O, P, right? So any labeling. Okay, and this is the H-group. The group of symmetry of the square. It happens in S. In Sn, you have many copies.
Subgroups of order are
And D4.
But it isn't.
Yeah, they're all D4. They're all a copy of D4. D4 is an abstract. Just as you say Z mod 2Z, it's an abstract. Okay, so now you know we can write D4 as subgroup of S4, and in general, what is meant by D4 is the labeling 1, 2, 3, 4. This is not a convention. This is not a. Okay. Oh, my head. Could you please show how to find the 3 variations of D4? Sure, I will do that. Okay, but yeah, yes. Rho is injective. Exactly. So rho G has the same size as G. Okay. Why is rho injective? Because the kernel is exactly. Okay. So suppose that and G is equal to G, right? If it's equal to EG, then B would be equal to 1. Agree?
Yeah.
What is the order of B? 2. Okay.
So if H was normal G, then the kernel could not be the identity.
The kernel is H. If H is normal in G, then the kernel is H. Very good question. That's a very good question. That's a very interesting question. So if I give you a normal subgroup on the and I tell you what's the kernel of the coset representation if H is normal, what is that? It's H itself. So the action of G on G mod H, what is, and then you get a homomorphism from G to the symmetric group. What is the kernel of this? This is the intersection of XH, X inverse, as H says in G. Now, if H were normal, what is the intersection of XH, X inverse? This is just H. That's a very good question. You see that or not? Yeah? No, not necessarily. No, it's not necessarily injective. Yeah, exactly. Well, yeah, usually it's the other way. If it's not normal, well, you could vary. You could like sometimes say, okay, so it can be injective, so the kernel is not the identity. Things like yeah. And I can give examples. But yeah, so this is a very good question. So a subgroup H is normal if and only if it is the kernel of its coset representation.
You read out.
Yeah, sure. A subgroup H, let G be a group, and H a subgroup of G. Show that H is a normal subgroup of G if and only if the action, the kernel of the coset, well, the kernel of the homomorphism induced by the action of G on G mod H, write it down, G star XH is GXH, is equal to H. I think the answer is shorter than the question itself, but okay.
Star XH equals GX.
Yeah, this is the action of G on G. Okay.
Last part is giveaway.
And then when do we use that? What proof did we use this? We showed something is normal by expressing it as the kernel of the coset representation. That's a very important proof as well. You remember it or not? You remember the proof or not? You remember the theorem we were trying to prove? We showed that a subgroup is normal if and we use this fact, we express it as the kernel of its own coset representation. Yes, hey? Not P group. Something has to do with prime. If H has index P, where P is the smallest divisor of the size of G, then H is normal. We express it as the kernel of its coset representation. And then the other one, if H is normal, then XH X inverse is equal to H for all X in G, and hence the intersection of XH X inverse is equal to H. Okay. Pretty cool. Very good. These are really good questions. These are really, really nice questions. Okay, so if you want, we can call it a day. Or if you want, I can do more practice questions. I have time. I could do more practice questions that are kind of more or less important. Oh yeah, Julian had a question. Yeah, Julian, yes, I'll answer your question. So how to find the question? How to find the subgroups of D4? Oh. Oh, by the way, there is a question that a lot of people were asking. The surjective, but I don't think anyone here asked it. The surjective homomorphism from S4 to S3, is that okay or not? I did that many times, but once I did not finish it, or the recording was cut. But is that clear? 25 times I've done that. The homomorphism from S4 to S3. The surjective one using many possible actions. Okay. So, okay, so just for the people attending, do you guys attending virtually, do you guys like a practice final or not? And here, do you want a practice final or just exercises?
I think like exercises for like topic, like I don't know, like 2-3 questions for like this topic, this topic, this topic. I feel like it's more like specialized.
That's like 30 questions I have to write.
Something.
Practice final is good. Okay.
Whatever you want.
Yeah, I'm just taking the opinion. At the end, I'll do what I think. Just tomorrow is Friday, weekend, so I would just give it on Tuesday, maybe 1 day before. It's not gonna be the practice finals. Okay. Yeah, so I'll give you the practice final.
See, being waiting for the final cover.
I'd say it covers the topics would be like 70 to 80%. I just want to give numbers, but you could sit down and write it, and you could assume it's a final. You need the proof. You need the proof of something. No. It doesn't. So that's a good point. Doesn't mean that the question will not reappear, and it does not mean that a question will reappear. So I could give you a question on the practice final, and it could be the same on the final, or I could just give it all different, but the topics are the same. Okay, so it's nothing. It's not the same with numbers change. That's it. Yeah. Yes, I'll give you like 10 problems, and then I'll post them maybe tomorrow, and then I'll go through them on Tuesday. Second and third, you should note how to prove them, and you should state the 3 of them. But yeah, practice final is so the only way I think it could be helpful, personally, is just by you sitting there and do it for 3 hours. A lot of the proofs you'll have the answers in the notes. Like, because I will do it the same. So I'll put 3 proofs from the notes at the beginning, and then exercises. It's kind of gonna be, the difficulty is almost the same thing, but you just have to sit down and do it. And it's more like a practice test for 3 hours. You sit down 3 hours, and you see, okay, how much I can do. That's the whole point. How much I can do with not looking at the book. I don't want you to take the practice final study guide, because if you do that, it's gonna go horrible. Trust me, it's gonna go very bad. You look at the practice final, you just know the do of the question and the practice final. I change a number. Boom. Yeah. Yeah. Okay. Okay. Sure. Yeah. That's a very. Yeah. Sure. I can post that. Yeah.
Will there be solutions to the rest of like these ones that we didn't do today?
Or can you do them next week?
I could try and do them next week, or I could do them now if you guys want. I could do them. Pardon me? What time is it now? Oh yeah, we can sub at 8. Yeah, definitely. Yeah, I forgot like the other questions, but if you guys have questions and the people there have questions. What's exercise for? Oh, show that if two permutations are conjugate, then they have the same number of fixed points? Is that the one? Yeah, okay, that's a very good question. Excellent. Show that if sigma 1, sigma 2 are in SN, then and sigma 1, sigma 2 are conjugate. Show that sigma 1 and sigma 2 have the same number of fixed points. That's a very, we know what a fixed point is, right? In this case. Basically, x is actually a fixed point of sigma if sigma of x is equal to x. Okay, why is that? If sigma 1 and sigma 2 are conjugate to each other, why do they have the same number of fixed points? Yeah,
So when you write them as like the disjoint cycles, the number of fixed points is just like n minus the length, and a conjugate, they have the same like cycle type, because they have the same length. So the number of fixed points is the same.
yeah, so the number of fixed points is just the number of cycles of length.
Write them as disjoint cycles, it's gonna move all those and not move all the other ones, so it's just n minus the length. Of like all those numbers.
You mean n minus the sum of the length?
Yeah,
Or,
minus the length.
very good, or another way, express it in another easier way, very good. What is the length of a cycle of a fixed point? 1, right? You see that? So if sigma is an S5, 1, 2, 3, 4. Okay? X is a fixed point. The number of fixed points is the number of cycles of length 1. Is that clear?
Yeah, I guess normally we don't write the single one.
Exactly.
So it's just n minus.
Exactly. And minus the sum of the, yeah. You can do it in this way. So sigma 1 and sigma 2 are conjugate. Implies sigma 1, sigma 2 have the same cycle structure, This implies that sigma 1, sigma 2 have same number of cycles of length 1. Implies same number of fixed points. That question could go on 10 marks. That question could go on 10 marks. And it's simple. If you know how to go about that. If you try not to think about this, if you try to do it in another way, it's going to be a bit harder. Okay, is it hard? I mean, it's so for example, if I were to give a hint, if I were to put this on an exam, doesn't mean it's not, but I'm saying if you have a question like that on an exam, I will give a hint, of course. I would say, look at the cycle structure of sigma 1 and sigma 2. Yeah.
Do you know why they're conjugate at that? Like I already had the result, but I didn't know the proof.
I think the proof is in the homework, and then the proof is very tedious. So okay, so and then if
So
you
you know
ask,
the results in them.
no, I said this one. No, the result is enough because if I have to write the proof, I would say like 15 minutes, and you have a lot of symbols. So first you do it for cycles. This is not bad, and then you extend it to product of disjoint cycles. This is the way to. So you prove that two cycles of length n are conjugate to each other. And then you try to generalize it by showing that if you have a permutation, you can write as a product of disjoint cycles. So you show that if the harder part is if they have the same cycle structure, then they must be conjugate. The other part is easier. If they have the same length, if they have the same cycle structure, if they're conjugate, then they have the same cycle structure. That's easier. But the other way is around. If they have the same cycle structure, you have to construct the sigma that makes them conjugate to each other. And that's a bit It's not like very, 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 very tedious, but it's just like a lot of notations. You just have to make sure not to mess it up.
So it's G1 and, I mean, the cycle have the same number of cycles of length 1, right?
Yeah. Any other questions? I think we're done this one, or we have still things to do. I don't know what I did. I mean, the other question just come from the previous. Oh shoot, 3.
Actually, can we prove that two things are isomorphic by just drawing a Cayley table?
So you show that they have the same multiplication. Yeah, you could do that. I think, but I mean, you have to define your isomorphism first, and then but I won't ask you to do that, right? Because I didn't do Cayley tables in class.
That's like way more, like that's way more simple. You just like write out all the things.
Yeah, but
and
I
then
give you
do it from, like 1 to
64 elements. 64 elements. Or even Q8, for example. Or this one. This question. Show that if G is a non-abelian group of order 8 and has at least 2 elements of order 2. How would you do it with a Cayley table? Right?
Use subgroups of V4.
No, you don't know it's isomorphic, so subgroup. You don't know it's isomorphic. Right? But you could show it if G has exactly, in this case, if G has exactly 1 element of order 2, you still have to do the math. You still have to do some math. And then you can show that G is isomorphic to Q8 in that case. So say G is a non-abelian group of order 8 with exactly 1 element of order. Then I think you can show it this way. You can write down a Cayley table. But again, it becomes useless, right? Because once you have the relations, you don't need a Cayley table. So the Cayley table, yeah, sure. But yeah, and then you have to fill 64 of. Yeah, I mean, but I won't ask you something where you have to do a long proof. It's gonna be a lot of them might lead through group actions. Show that G is isomorphic to this, find a group action, boom. That's how you. I mean, okay, so do people have more questions, or I'll answer the. Okay. Do people have more questions?
So for the question 4, we just need to write this word.
Exactly.
Like I got 2 points.
If you have something that you're on an exam, yeah. A lot of the questions are just testing if you know the basic concepts. And again, I don't give you I don't give you like extra space for your work. All of it should fit in one page, and you can use the back of the page if you want to do rough work. But I don't give you extra space. Everything should fit inside the thing I give you. So it's not supposed to be very long. And if you studied really well, an hour should be enough. Well, sigma 1 is a permutation, it's not a subgroup, it's not a group. Right? Okay, the so if they're conjugate, no, I mean the subgroup generated by sigma 1 is isomorphic to the subgroup generated by sigma 2. But that doesn't mean anything. Right? That doesn't mean in that case. Well, it could. But that's don't they have the same cycle structure if they're conjugate? And number of fixed points is just the same cycles of length, the number of cycles of length 1. So it's perfectly valid proof. It's a valid argument. Okay, so do we have questions? Yeah,
So you said homework at the beginning during exercises 1 and 2, or was it just exercise 2 parts 1?
no, exercise 1 and exercise 2 entirely. I didn't do all of them, but 1 and 2 are very important from exercise 2. But 3 in exercise 2 is very important. Very important. The index P thing is normal if P is the smallest prime divisor, and problems 1 and parts 1 and 2 from exercise 1 are also important. No, I'll propose the solutions. Yeah. No, you just have to use it. I won't ask you for the proof. The proof? No. Just the same. No, I said Cauchy's theorem that you don't have to use the proof, right? Yeah, I said yeah. Yeah. Sure. Any other questions? Yeah. Yeah, you need to know the proofs of these, because maybe I might not tell you proof Fermat, but I might tell you something a bit similar. Okay, I might show something a bit similar to it. Okay, so I mean in fields you will see, but if I were, so the exam is on 17. Okay, so what I would say, my humble opinion, and the way I did the exam, 65 on 70 can be done with post-midterm material. And that makes sense because 30 question is on groups, right? 30 questions on 30 points are in rings. And then from the 40, I'd say one question you can do with the pre-midterm material entirely, or maybe most of them, or a tiny bit. You still need the pre-midterm material, but depends on what method you use. Okay, this is my opinion. It's not again. So someone told me that I should expect that whenever a method uses a group action, that it will be less used. That's what I've been told. But I do it with I did many questions with group actions. Okay, so
Is it shorter with group actions?
pardon me.
Is it shorter?
Not necessarily shorter. Some parts may be shorter, some parts may be longer. Some parts you just need to use the right statement. If you use the right statement, it's gonna be quick. If you go through it again with what you know from before, it's gonna be a bit longer, but it might feel easier. Yeah.
By like choosing to use group actions, it's like make a group action so that it induces a homework one.
Depends. You will see. Okay. Depends. Okay, like it depends. Sometimes yeah. Sometimes
Because
yeah.
how else would you like apply group actions if it doesn't bring out group actions?
For example, show that the normalizer of, I tell you first question, show that G acts on the conjugates of H. G star X H X inverse is G X H X inverse G inverse. Okay. And then I tell you what is the size, find the normalizer of H, where H is a subgroup of order 8 in S4. First you have to show that it's a normal, right? You know you have 3 subgroups of order 8 in S4. So the normalizer of H has index 3. And this is how you use a group action. Normalizer, so you use the orbit stabilizer theorem, that G, the index of the stabilizer, is the size of the orbit. That's one way to do it. Okay. And then you can, if I tell you find a surjective homomorphism from, I don't know, find a homomorphism from like these questions. Okay, you have to use a group action, for example. Okay, it doesn't mean it's the only way, but might be. Okay, like it's not the, like I leave you many ways to I try to leave an escape, you know, like if you don't want to use group action, you can use another method, but it's a bit longer and requires the knowledge of previous material. Okay, so it's again, you should be comfortable with Lagrange, the ideas of Lagrange, the ideas of cosets, and then I think you should be fine. Okay, it's not, and don't be intimidated by big numbers. Okay, if I give you a big number, don't be intimidated by it. Okay. So if I tell you what are the subgroups of S to the 3 million, you know what are the subgroups of that? It's 1, A to the 3 million, and S to the 3 million. Okay. If I ask you a question, what are the normal subgroups of S to the 3 million? Don't be intimidated. I tell you, like, state, write down without justification the normal subgroups of S to the 3 million. 1, A to the 3 million, S to the 3 million. So if you have a big number, don't be intimidated. Okay. And yeah, I mean, normal subgroup of S to the 3 million. If I tell you what are the normal subgroups of S to the 3 million, then, or I tell you find a homomorphism from S to the 3 million to Z mod 2Z that is surjective. You know that S to the 3 million has a normal subgroup of order A of index 2, which is A to the 3 million, and the quotient group is isomorphic to Z mod 2Z. Okay, so if I give a big number, don't be intimidated by that. Okay, you should just be you should be able to do the question. You should be able to do the question without the number itself. Okay, just to, yeah. Okay, don't be intimidated by very big numbers. Should I decide to do that? But for example, if I tell you, I don't know, but anyways, okay. Again, I don't expect it to be really tough, honestly. So it's I know people are more worried than usual, but hopefully, yeah.
I guess what you said about question 1, are you doing that one?
The S4, I did them. I mean, S5 I didn't do, but it's the same idea as S4, right? Same idea. Just have to count the cycles. I can pose a solution if you want. Yeah, I can write down the solution, but I won't justify it. I'll just tell you what the size is, and then, yeah. Okay, yeah.
So to redirect coset representation, can you give us like an example where we would have to redirect coset representation in order to finish it?
No, I will tell you derive it.
Oh, you
I'll tell you, yeah, rederive it. I'll tell you rederive it.
How much more expensive?
Just what you need. You use your judgment. Okay. You don't have to show it's a group action. Just say, okay, G on G mod H is a group action. I know it's a group action. And yeah, you could assume that the kernel is the intersection of the conjugates, for example. You could assume. So G acts on G mod. This is what I mean. G acts on G, unless I tell you prove all of the things, but this is what I mean. Redirect it. G acts on G mod H by G star XH is GXH. This action induces a homomorphism from G to the symmetric group of G mod H, whose kernel is the intersection as X belongs to G of XH X inverse, which is contained in H. That's this 2 lines what I want. Okay, unless what I tell you is that rederive it entirely. Yeah. No. Immediately. If it's induced by the group action. Yeah, immediately. Unless I tell you, unless the question explicitly states, show that if G acts on S, that the action of G on S induces a group homomorphism from G, the symmetric group on S. If that's the question, that would be a regroup from the nodes, right? A recap from the nodes. Then you'd have to do it immediately. Then you have to do it step by step. Okay, and I'll give you the step. I'll tell you first, show that lambda G is an element of the symmetric group of S, where lambda G of S is G star S. And then I'll tell you, show that the map G to lambda G is a homomorphism. 3, show that the kernel of the homomorphism is the intersection of the stabilizers. Okay, I would give you the steps because 1, it's easier for me to grade. 2, I don't want you to miss if you have something that you didn't show, I don't want you to miss the notes. Okay, you can, and then again, if there's a question you can't answer, you can answer part A, and you feel you need part A and part B, assume part A. Okay, don't say I didn't get it, so no, assume part A and then proceed. Okay. Okay, let's okay, great. Let's do that. Let's do any group of order p squared is abelian. Let's okay. I mean, I'll give you something that could be a question, a very nice type of question. Let P be a prime, and G a group of order p squared. Okay, 1. Show that G is abelian. 2. So if you have a group of order p squared, very good question. These are very typical questions.
If you use a theorem, you solve this.
Someone you saw in the tutorial, you might have seen the fundamental theorem of abelian groups, but you can't use it because it's not good. I'll tell you, do not use the structure theorem for the. Yeah, no, I usually pay attention to these things. So do not use the structure theorem for finite abelian groups if you know it. Okay. But how do you do this? So if you have a group of order p squared, here you have to use Cauchy's theorem, you have to use every single thing here, which is very, very. I mean, and even I don't think you need the first one for the second, but anyways, you still can. They said you don't need the first because you can use the index p business. Okay, but anyways. So show that G is abelian. So what is ZG? The size of ZG belongs to 1 p squared, right? Can ZG be equal to 1? It's a p group. G is a p group. So what? So ZG strictly recurrent. Agreed? Now, can ZG be equal to P? If ZG is equal to P. ZG is a normal subgroup of G. So G mod ZG is a group of order P. Agree or not? If it's a group of order P, this means that G mod ZG is isomorphic to Z mod PZ, which is cyclic. Agree? So G is abelian. Agree? If G mod ZG is cyclic, then G is abelian. So ZG is G. This means that the index of ZG is p squared. So ZG, or sorry, the size of ZG is p squared. Contradiction. Okay. Hence, it must be the case that ZG is a size p squared. So ZG is G.
What is it? And what P?
Pardon me.
Why was the size of C P?
Suppose it were P.
Yeah.
Then G mod ZG would be cyclic. If G mod ZG would be cyclic, then G would be abelian. Homework 6. If G is abelian, then ZG would be equal to G.
Oh.
So ZG would have size P squared. Contradicts the fact that ZG is. Okay, hence G is abelian. Great. Now, 2. That's a very, very, very good question. Show that G is isomorphic to Z mod P squared Z, or G is isomorphic to ZP cross Z. We could do it with abelian, we could do it without abelian. We could do it with 1, we could do it without 1. Decide, what do you want?
What's the shorter?
Both are equally, both are not bad. Maybe without 1, you don't use this, but you use a property of index P, where P is the smallest prime is normal. Pardon me? The general one, what do you mean? I mean, let's try. Okay, so what's if G has an element of order P squared, then G is cyclic of order P squared. And hence okay, that's the first one. Now, if G has no element of order P squared, what can I say about the order of the elements of G? If G has no element of order P squared, what are the possible order of elements in G? You have 1, and you have P, and you have P squared since P is prime, right? Those are all the divisor of P. Now, if I tell you that you don't have an element of order P squared, what are the possible orders? 1 and P. How many elements of order 1 you have? 1 element of order 1. So if G has no elements of order P squared, then any non-identity element in G has order P is fine. Okay. Now, if any non-identity element has order P, you agree that I can find 2 elements, X and Y, both of order P, such that Y doesn't belong to the subgroup generated by X. Agree with this? So how many elements of order P you have here? P squared minus 1. Agree or not? How many subgroups of order P you have? A bit more than P. Slightly more than P. So in the subgroup of order P, all the non-identity elements, how many elements of order P you have in a subgroup of order P if P is prime? P minus 1, right? Because you have the identity of order 1 and all the remaining ones have order P. So every subgroup of order P must have P minus 1 elements of order P and 1 element of order 1. And if you have 2 distinct subgroups of order P, they must intersect at the identity because P is prime. So the intersection is either the identity or both of them are equal. Now, in that case, you will have P plus 1 subgroups of order P. Because every subgroup will contribute to P minus 1 elements of order P. Okay, but anyways, you don't have to do that. Why the last line is true? If G had no element of order P squared, what are the possible orders of elements in G? These are the possible orders or the divisor. That doesn't mean, so it's 1 P or P squared. That doesn't mean you have an element of each order. But if it has no elements of order P squared, then every element must have order 1 or P. Now, what's the only element of order 1? Identity. So any non-identity element must have order. Is that clear? Yeah. So take xy hence. Let xy be G. Have order P. With X not belonging to the subgroup generated by Y. right? Because you can find at least two subgroups of order P. You agree with this? How many elements are there in Y? How many elements there are in Y? The subgroup generated by Y. P, right? How many elements does G have? P squared. You can pick an element in G that is not in Y, right? What's the order of that element in that case? By assumption. P. Okay? So X has order P with X doesn't belong to Y. Now, that's a very cool thing. We can do it with the previous one. Since G is abelian, X and Y are both normal. So let H and K is Y. So if since G is abelian, both of them are normal because any subgroup of an abelian group is normal. Or you can look at the index. What is the index of H? What is the index of H? H has size P. What is its index? P squared divided by P, which is P. What is the smallest prime divisor of G? G has size P squared. What is the smallest prime divisor of the size of G? P. If you have a subgroup of index, the smallest size of index, smallest prime divisor of a group, what can you say about that? It's normal. Okay? So that's another way to do it. So H is normal in G. K is normal in G. The intersection of H intersection K, what is it in this case? It divides P. Agree or not? Divides P. Divides P. So now, if it's equal to P, then what can you say? Then H is equal to K. If H intersection K is equal to P, then H is K. Hence, H intersection K S has 1, implying that H intersection K is the identity. Right? Since P is prime. Now we have two normal subgroup. What is the size of H times K? It's P squared. HK is a subgroup of G. Hence, it's a subgroup of G of size. HK is H times K. One. P squared. So G is equal to HK. Now both of them are normal and they intersect at 1. They're both isomorphic to H cross K. Since H is normal in G, K is normal in G. H is isomorphic to Z must be Z. K is isomorphic to Z must be Z. Boom. Okay? This is a very fair question. Okay, so I will turn the chat off. I'll turn the video recording off. I will post it on Wednesday, unless someone can help me, like with the charger. I prefer this.
You must. Where is it? Oh, there's one where is it?
It goes off. Okay. This is one very, very good question. All of these questions are like really exam type questions. So So what I said is the final will be posted on, when did I say? Wednesday. The last after the last hour of lectures. Okay, it will be posted, and then you have to try it. Sit there for 3 hours, and don't like go see your notes, and just take it as I have to do it in 3 hours. I have to figure it out in 3 hours. Okay, try to. This is my advice to you. Again, you're free to do whatever you want, but this is my advice to you. Sit there and do it. Okay, 3 hours. Give yourself 3 hours and do it. Yeah. Exactly. Okay. Just I have to answer the D4 question. So how do I get the labeling of D4? The symmetries of the square. Now, if I get the symmetries, you're still with us? The person who asked the question, are you still with us? Anyways, I'll just explain it. So how do you find the symmetries of this one? You label it 1, 2, 3, 4. Now you want to find another labeling here to find the other symmetries. So what's a good idea to do? Just 1, 2, 4, 3. Now if you want to find a third labeling, you can find a third labeling, which is 1, 4, 3, 2. And you look at the symmetries of this one. Yeah. Okay. Is that clear? Now try to write any other labeling. Can anyone here suggest another labeling of the square? Start somewhere. 1, 4, 2, 3. Can you find it? It's here, right? Another labeling. Anyone can give me another labeling? Don't start with 1. Start with something else. 2, 3, 1, 4. There it is. Okay. So the square really, how do you find? You choose your two opposite points. Just choose two opposite points and label them. And that's how you get the labeling. Okay, is that clear? Is that clear? Okay, so these are the three labelings that you have, and you find the symmetry of this figure. And then with the square, what you just find the symmetries. So what is the symmetries of this square? You have a rotation. So the rotation, let's do it for the square. The rotation, 1, 2, 3, 4. You rotate everything by 90 degrees, you get a symmetry of the square. So it's 1, 2, 3, 4. Then you have the square of that, which is 1, 3, 2, 4. By the way, are you guys going to tutorials or not? Are you going? Did you go today or yesterday? Sorry, or Monday? Yeah. Okay. So please go to tutorials. Okay. It's the so 1, 3, 2, 4, and then you have the cube of the rotation, which is 1, 4, 3, 2. This is rotation by 270 degrees. This is rotation by 180 degrees. This is rotation by 90 degrees. This is the rotation by the identity by 0 degrees. Now you have the vertical reflection, which is 1, 2, 3, 4. And then you have the horizontal reflection, which is 1, 4, 2, 3. So you have the diagonal reflection through 1 and 3. So this gives you 2, 4. And you have the diagonal reflection and 4. This gives you 1. Is that good? Shivam, is that good? Yeah. What do you mean? Yeah. Oh, how I find them? Vertical, reflect this vertically. What do you mean?
Putting it in bracket.
Sure. You read the vertical reflection. what does one under this vertical reflect the square? Where does one go to? Where does two go to? 1 to 2. Where does 3 go to? Where does 4 go to? Great. Now let's look at D1, the reflection through 1, 3. Under this reflection, what happens to 1?
Oh, like that.
Reflection on to this line. So you draw a perpendicular to this line and you look at the opposite. Symmetry axial. No. Okay, so you're reflecting through a line, and you want to find the image of this point. Okay, you drop a perpendicular, but it is the same size. Okay, so if a point belongs to the line, what is its symmetry with respect to the line?
Oh, it's not.
Yeah, okay. Like this. You have a line here. Okay, you're gonna find the symmetric of this point with respect to this line. You drop a perpendicular. And this is the reflection of this point to this line. If you have a point on this line, what's this reflex? This one.
So it's,
Okay.
yeah.
How can you just a perpendicular from here to here? It's this one. Okay, so D1, how do you 1, where does 1 go to? 3, where does 3 go to? 2, where does it go to? 4, where does it go to? Okay, here. D2 reflection through to 4. What happens to 1? Goes to 3. Where does 3 go to? 1. Where does 2 go to? Where does 4 go to? What do you get? Okay. Okay, any more question, guys? The people attending online? Okay, so let's end this.